Good day. I'm Vincent Saxtetter, and this is my channel, After the Age of Fire. Today I'll be talking about the first actual technical material of this channel. The first, not terribly technical. I'll just be going into numbers for the first time. And the numbers I'll be talking about are very important numbers. They're, they describe how the human race has been consuming more and more, roughly twice as much every 22 years for the last 250 years. And I just want to set that out for you because it just frames our situation, and I just want to make it very clear that there's really no arguing with the fact that we've been multiplying our resource use or about how fast it's been going. Um, but first, before I launch into that, I want to say a word about what exponential growth is, because that's what we've been doing. When something multiplies over and over again, it's generally exponential growth. Now, I want to say just very simply, what is exponential growth? It's a mathematical pattern where, and the way that you can tell that exponential growth is happening is if you measure something always at the same time interval. Say every hour you measure something, after 1 hour, after 2 hours, after 3 hours, after 4 hours, or it could be days or years, or it could be, it could be 1.5 hours. So every 1.5 hours, and then so you measured after 1.5 hours, then after 3 hours, after 4.5, after 6. Just have to make sure that the increments are equal. Measure, and that's the first step in figuring out whether something's doing exponential growth. And the second thing is to check, after you've measured this quantity, whether it's always, after each time interval, whether it's actually grown by, whether it's multiplied by a certain amount. So if something is twice as big as it was yesterday, okay, and then I wait another day and it's twice as big again, and I wait another day and it's twice as big again, then that's exponential growth. Okay. On the other hand, if something's twice as big today as it was yesterday, then I wait another day and it's the same as it is today, that wouldn't be exponential growth. Uh, it has to be a regular pattern of multiplying. Exponential growth, put simply, is just multiplying something over and over again. So, and there are many processes in the world around us that do undergo exponential growth. For instance, bacteria, if you put them in a petri dish, um, then for some time, until they basically run out of space and food, they'll multiply exponentially, the number of them. There's another example of, you take an egg inside the womb, a fertilized egg, and during the first few days, the number of cells in that egg, the egg is not yet really implanted on the side of the womb, so it's not going to get any bigger. But what it will do is it'll divide into 2, and then into 4, and then into 8. So if you count the number of cells in that living being, the number of cells will multiply. Will be going through exponential growth. Um, Another example is the speed of our computers, and this is a piece of history. The central computing unit, the unit that does the math and makes the decisions for a computer, and is called a CPU, and the central processing unit, and it does an action every time interval. And the question is, how many operations can a CPU do in a second? Okay. So when CPUs were first invented, and by the way, CPUs are not just inside of computers, but there's very similar things inside of your watch and inside of your cell phone. So when we're talking about the speed of a computer, we're also talking about the speed of your watch or your cell phone. or any other thing, say your washing machine nowadays or your car. Um, when CPUs were first invented just before 1970, well, by 1971 they were able to do about 1 million operations per second. And the speed with which they were able to do them multiplied. It began to multiply over and over again. And by 1990, they ran 100 times as fast. So over 19 years, the speed of computers multiplied by 100. And if you were to look at years in between, you would have found a trend. The multiplication, you would have found that every 2 or 3 years, the speed multiplied by 2. Now that trend continued, and in fact by 1990, or actually much earlier, people could see there was a trend, and they could begin to make reasonable guesses or predictions about what the speed of CPUs would be after another 2 years or another 10 years. And so this kept going, and it wasn't just that they multiplied by 100 during during the first 19 years, but from 1990 until 2002, the speed of computers multiplied by another 35. So the overall speed multiplication from 1971 to 2002 was a factor of 3,500. It was immense, and the reason why computers and cell phones and all the other computing devices can do all the things they do for us is because this multiplication happened. Now, in 2002, the multiplication ended, and since then the speed of CPUs and of our computers has remained more or less the same. So the exponential growth of in other words, our speeding up our computers only lasted about 31 years. And there's a simple reason for that. The reason is that the faster a computer goes, the more energy it uses, and the more heat, and because it's using more energy, the more heat it produces. And so as you increase the computer's speed, it gets hotter. The CPU part of it, which is a small thing, well, the actual chip inside the CPU might be a couple centimeters wide, I guess, and then the housing around it will be 8 or 10 centimeters wide. That CPU produces more and more heat, and after a while it just becomes very difficult to keep it cool, because it's like a roaring fire inside of a small little piece of real estate inside your computer, and so you can. And the other problem is, of course, that CPUs do melt if you make them hot enough. In fact, once you get a CPU to about boiling temperature, it tends to stop working so well. So our computers have throttles inside of them nowadays built so that if a CPU begins to get close to boiling temperature, water's boiling temperature, the computer will deliberately slow itself down so it will do less work. Okay. So that's how CPU speed multiplied exponentially for 31 years, and that's why it stopped, and why you can make CPUs a little faster if you immerse them in something very cold, or people make water-cooled computers where you have to somehow cool the CPU with water going right past that part of the computer without getting the whole computer wet, and you can get a certain amount of speed improvement that way. Not a huge increase, and you get a rather expensive computer, which looks very cool. But again, you aren't going to get that much more speed out of your CPU that way. So there are other things that increase exponentially. if somebody's if people are passing a disease from one to another, it can happen that the number of people with that disease multiplies by a certain number every few days in an epidemic. It doesn't always happen that way. COVID seemed to be doing something like that for a while, but actually, I'll come to this later. It never actually, it was multiplying, but it wasn't multiplying by the same number every, say, 3 days. So it didn't quite match the 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 pattern called exponential growth. Exponential growth is a very specific mathematical pattern, and it's a very special one because once you know that something's pursuing obeying exponential growth, you can make very good predictions about what's going to happen as long as that exponential growth continues. You just count. You say, okay, well, I know that it's multiplying by 2, and I'm going to over and over again come back to this notion of multiplying by 2 and the length of time that it takes to multiply by 2, called the doubling time. It's just a simple way. The doubling time is a simple way of describing how fast the exponential growth is going. If your doubling time is 1 day, then you know that after 10 days it will have multiplied by 2 10 times, and so it'll be roughly 1,000 times bigger than it was at the beginning. On the other hand, if the doubling time is 1,000,000 years, then say something having to do with astronomy, then it'll take 10,000,000 years before the thing multiplies by 1,000. But anyway, for that period, as if it really is obeying exponential growth, then you can make a prediction for how big this thing is any time in the future. Just count the number of time intervals that you want to predict. And say I want to predict for after 5 doubling times how much bigger this will be. Well, 5 doubling times, let's say the doubling time is a week now, and I know the doubling time is a week, so after 5 weeks, then I will have multiplied by 2 5 times, so 2 times 2 times 2 times 2 times 2 is 32, so it'll be 32 times bigger. So I want to say a few more words about exponential growth. One is it happens only in special circumstances and in special situations. Basically, situations where 2 things are in force at the same time. So there are 2 requirements for exponential growth. One is that there are resources in excess of the needs. You have more resources than you have needs. So there's plenty of something to go around. So for instance, if you have a disease that's spreading and there are plenty of people around who have never acquired the disease and don't have immunity against it, then there's plenty of resources for that disease to continue its growth. Okay. And the second condition of exponential growth is that the second requirement is that there should be no control over the growth. So there's plenty of resources for it to consume, and there's no control, no brake on it. So I mean, I could put a brake on a disease's exponential growth by simply staying far away from, keeping people far away from the people who are sick. And sometimes that has worked. Not always, but in some cases people have been able to, especially when there were just, say, 100 people who were sick, to isolate them from the rest of the world and be very careful about people going back and forth between them, and to create barriers that prevented the disease from growing. It doesn't always work, as we know very well from recent history, but it can work. Um, uh, so what if you have resources, plenty of resources, much more resources, fertile ground, and you have no control over the growth, then so nothing's holding it back, then it can very well happen that something grows exponentially. There are other mathematical patterns that something could follow. Um, uh, Exponential growth is not the only way that something can grow, but if you see exponential growth, you know that it's out of control and that it has plenty of something available for it, plenty of what it needs. It's a very mechanical process. It's really no thinking involved in exponential growth. Uh, it's if it's happening, it means that something's just going as fast as it can, no control, and 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 a very simple thing is happening over and over again. You don't get a very simple mathematical operation, namely multiplication, over and over again, unless the reason for that is also very simple. Um, it's something that atoms can do. For instance, in a nuclear reaction, atoms can can in some circumstances go through exponential growth, and that can produce a sudden release of energy and of heat. Say in a nuclear bomb, uh, but there are so I'm just emphasizing that it's something very mechanical. It's something that bacteria can do. It's something that viruses can do. It's something that um, you know, atoms and inanimate objects can do. It's not something that signals or should give you much faith when you see exponential growth. It actually should be a hint that whatever is going on is really simple-minded and does not require a living process to push it along. Um, there's no thinking going on, is what I'm saying. Um, so another word I want to say about exponential growth, about when you see something multiplying on a schedule, it just keeps multiplying, say every 3 months or every week, um, then if it continues that exponential growth, it will eventually just take over the world. Okay, it may seem small at the time. In fact, usually when you're witnessing exponential growth, if you're witnessing it at all, um, it will seem insignificant. Um, this isn't this is analogy. I'm not pretending to suggest that weeds go through exponential growth. For all I know, in some circumstances they may, but it's certainly the case that if you have a garden uh, and you watch the weeds, that for a while you'll see very tiny weeds that look like they're completely insignificant, and then the day will come where you'll realize that the weeds have outgrown whatever you're trying to grow. And the transition between insignificant weeds and weeds that are way too big and way too hard to pull out is really fast. You'll have seen the weeds already weeks or a month or two ahead of time, and it will have seemed like they were okay during that in fact it seemed like too much trouble to go picking out tiny little things out of the dirt, until suddenly, very suddenly, in some days or a week, you realize that your crops or whatever you're growing is just dead or very close to dying, and also you have a huge task on your hand, because now the weeds are not things you can pick out with a couple fingers. Now you have to tug on them or dig them. Um, that's the way exponential growth is. It looks like nothing until suddenly it takes over the world. Um, but we can go from that to a conclusion, another step in the logic, which is that no exponential growth lasts forever. So, for instance, for CPU speed, it was clear already, as soon as people noticed exponential growth, that it couldn't go on forever. It if it had gone on forever, you would have gotten infinitely fast computers and ones that produce an infinite amount of heat, even faster than a nuclear bomb does, and uh, and so on. And it's obvious that it can't work. Okay, or if you have a disease that's spreading, one very obvious limit to any disease is that, say it's one that infects humans, is that it will never infect more humans than are alive. Okay, so right now that's around 8 billion. So you have it may, you could calculate, exponential growth would mean, okay, well, after, say, every month it'll multiply by 2, and so you certainly there's a day, if it's following exponential growth, you can calculate the day or the week or the month when, if it continued multiplying by 2, the number of diseases would be larger than the population of the human race. And from all that, you could conclude that by that date, exponential growth will have ended. It's not like people will suddenly materialize into an existence in order to keep the disease growing. So overall, I'm saying, I'm making a couple points. Is I said that if you do see exponential growth, it's a really simple-minded thing. It signifies that something is out of control, and whatever it is, it's not thinking about it. It's just going as fast as it can. Okay, and it has plenty of resources. And the second thing is that the second point I'm making is that all exponential growth ends, and generally it's the end of its growth has something to do with a lack of resources. For instance, the CPU speed stopped multiplying because we ran out of ways to keep a CPU cool. So this is just going over. I've just been trying to describe what I mean by exponential growth. I just mean multiplying by 2 on a schedule, or could be multiplying by any number on a schedule as long as it just keeps multiplying by that number over and over again at regular time intervals. Now, I bring this all up because I want to talk about, and this is a core fact about the human race. It'll be core to this channel, to everything I say. The core fact is that from roughly 1780 until now, the human race has been doing exponential growth. I don't mean growth in the number of people. In fact, actually, the number of people is not multiplying, and it looks like it may well in the next decades just start decreasing. But the human population never multiplied on a schedule. You can talk about multiplications over the last couple hundred years, but it certainly wasn't on a schedule, and the number of multiplications of the human race is far smaller than the number of multiplications of our resource consumption. The human race is multiplied by, I think, roughly 8 in the last 200 years and 250 years, and our resource consumption is multiplied by something more like 1,000. So there's really no comparison between, first of all, our population is not and never has gone through exponential growth, while our resource consumption has been and continues to go through exponential growth. It continues to multiply. Now, I said it's a regular pattern executed on a schedule, same multiplier every time interval. For the human race, it's not exactly the same multiplier every X years, every, say, um, every say um, um, 22 years, but it's close enough, and it's been going on long enough, close enough to a regular multiplier, and it's been going on long enough that we can see that the whole pattern has been more or less exponential since 1780. Okay. And I'll discuss that in some details in the remainder of this video. And then I want to start by talking about our energy use, because we have data going back to 1800 about our energy use, and we don't have such data going back so far for other kinds of resources that we consume. So first I'll talk about energy, which certainly has been multiplying pretty regularly, and then I'll end by discussing some of the other resources and how they've been multiplying. For energy, I'm going to talk about only coal, oil, and gas. Okay, and I'm going to leave out renewables and nuclear. Whether you count that as a renewable or not, you can decide. Anyway, I'm going to leave them out because, in fact, even now they just provide a few percent, a very small fraction of our energy use, and in the past even a smaller percentage. So you can get the numbers right for our energy use without taking into account those things, and just makes life simpler. The data about renewables use doesn't go back as far, because in fact we didn't start using most of those renewables until pretty recently. Also, just you have to keep track of more things, and coal in particular has been an important thing for the human race for hundreds of years, and we have kept track of our use of coal. The Where was I? So the other thing that we're leaving out, that I'm leaving out, is our use of energy from our crops and our forests. That is an important, in fact, it's still about a quarter of our total energy use. A quarter of our total energy supply is from crops and forests, but actually we don't use it. We use very little of that supply for our cars or our electricity or whatever. There's a little bit that we do use for electricity and for biofuel, but a very small fraction of it goes for that. That's different from 300, 200 years ago, when all of our energy came from our crops and fuels. Just about all of it. There's a little bit of coal mining back then, but almost all of it came from crops, fuels, and so I'm going to leave that out. Okay, I just think the reason why I'm doing that, and the other thing I should say, is it's still a quarter of our, as I said, a quarter of our total energy consumption, and even in 1970, it was roughly a half of the human race's energy consumption. And before that, of course, we were using more energy from crops and fuel than we were from coal, oil, and gas until around 1970. But so it's a significant thing to I mean, if you added in coal, oil, and if you kept track of the crops and fuels along with coal, oil, and gas, you would say roughly that there's been only fairly small growth in our energy consumption until 1970, and then after 1970 things multiplied. But I think that's just a category error. The fact is, we use coal, oil, and gas for different things than we use our food for. In fact, most of our crops go for growing meat. We don't eat that much of it. So I think if we talk about energy use, it makes a lot of sense to concentrate on the coal, oil, and gas, leave out the crops and the wood, and we aren't using and then also since renewables are such a small fraction, it simplifies life a lot to just leave those out. So with those provisos, I'll go on and just give the history in a few minutes, a couple minutes, of what our energy use has been like. Okay, so we have to start with coal because for a while we weren't really pumping out oil and gas, um, and we have a history of coal use that goes back thousands of years, but we weren't mining very much of it, all things considered. And it wasn't until 1712 when Newcomen invented a steam engine, which was a way of a steam engine is that we began to be very interested in mining more coal. Um, and the reason why steam engines are so important, you know, if you didn't have it was the first engine in the sense that we talk about now. We know what we can do with engines. We can move things around. We can pump things. Um, we can run machines. Uh, and 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 before the engine, you know, all the things that we do with an engine. So the key wasn't that this was a steam engine as opposed to a gasoline engine. It wasn't that this engine was burning coal versus any other thing. It was just that he figured out how to make an engine, and um, and you could power it with wood. And I bet that some, in fact, even some trains were still being powered by wood decades later. You don't have to use coal. Um, but a steam engine is, you know, so as you know, and by our standards, they might look a little crude, um, but they were able to do amazing things that people really had a lot of difficulty doing before that. And one of them was running pumps, pumping water around. And in fact, I think that's what the first Newcomen steam engine was used for. Then for running a machine called a spinning jenny. A spinning jenny's job is to make thread. So women no longer had to do that, make their own thread. And it could run looms. So you could use the thread to make fabric. And the British became famous and rich for selling fabric around the world at, at low prices, large quantities of it, and low prices. So the spinning jennies and the looms. You could also use motors, engines for threshing grain, and then you could use them for milling grain. You could use them for running factories, and you could, sooner or later, people began to figure out how to use engines for transport, starting basically with railways, and then you could also use them for any number of other things. And as the British began to figure out how to do this, they became more and more interested in using engines. This was a British thing. That Newcomen was an Englishman, and the English became obsessed with figuring out what you could do with engines and with obtaining coal to power their engines. And so for the next, well, I think it was roughly 100 years, most of the world's coal that was burnt was being burned in England, nowhere else. Um, and the reason why they were so obsessed about it was because they were able to make money and get ahead and run an empire by using these engines. It was an extraordinary thing. Um, so if you look at the history of our coal usage and the energy produced from our coal, um, it's hard to say exactly when our coal and our energy usage began to grow exponentially, when it began to multiply. but it was somewhere, I think, between 1750 and 1780. So 1780 would be about 250 years ago. It could have been a little earlier, just there's not that good year by year data, so I can't tell for sure, and I don't think anybody can. But what is known is that between 1700 to 1815, the amount of coal that we mined and burned multiplied by 9. Um, so it, uh, roughly 3 doublings. 2 times 2 times 2 is 8, so that's not so far from 9. Um, then from 1815 to 1860, uh, that's 45 years there. It began to multiply by it was multiplying by 2 every 15 years. So we were exponentially growing our coal usage and our energy usage. The human race was, but specifically the English were. And our multiplier, our doubling time was 15 years during the first, and then every 16 years until 1913. So for the first more than century of our exponential growth, our doubling time was about 15 years. Now, all that time it was just a business of burning more and more coal. Okay, there was a change that that after a while, it wasn't just the English who were burning all the coal, but some other countries began to join in. First Germany, and then France and the United States, and also Japan. And this may that list of countries may intrigue your interest. And in fact, the countries that really drove and engaged World War I were the countries that had figured out what to do with large amounts of coal. The English remained the dominant users until sometime in the middle of the 1800s. Then other countries began to join in, and very quickly after that, the majority of the coal was being burned outside of the United Kingdom. So that's the first roughly 130 years of the human race's exponential growth, from sometime probably around 1780 until 1913, this multiplication by 2. Now, during that time, especially in the late 1800s and early 1900s, people were beginning to figure out what you could do with some gasoline. And even in 1800, they had figured out that you could take coal and generate from that coal a kind of gas, which you could force through pipes in your city and through people's houses and use to fuel lamps. So you had the gas lighting. You had people lighting. Gas lighting meant lighting gas lamps in your home or on the street, and there were lamplighters to do that. But that was at first coal gas that had been extracted from coal. Coal was also used. I emphasized the use of its use for engines, but it wasn't just used for engines and for gas lighting. It was also used for many other purposes. One of the most important was producing steel. Steel to make yet more engines, more machines, more factories. And it was a process that fed itself. You make more machines and you can get more coal. You get more coal and you can make more machines. Now, you may remember that World War I started in 1914 and ended in 1919, and it's a remarkable fact. And you may remember that World War I involved the deaths of huge numbers of European young men. And it's proved to fundamentally change the trajectory of the European nations. That they're still reeling under the impact of what happened during World War One. And I said that the exponential growth continued until 1913, and it's a remarkable fact that from 1913 until 1934, the world's energy use remained roughly constant. It didn't multiply. In 1934, the world's total energy use was not very different from the world's total energy use in 1913. It should have multiplied by 2 more than once, probably by 3 during those 20 years if it had kept going. No, not quite 3, somewhere between 2 and 3. If it had kept following the previous pattern, multiplying every 15 years or so. But it didn't, which is very noteworthy. And I don't remember running across anybody making anything out of this fact. And amidst fact, it's like the human race missing a heartbeat, or just missing a year's worth of heartbeats. If you see somebody, it's a pause of grandiose proportions. It might have something to do with the fact that until 1913, almost all of the world's use of coal was in Europe and in the United States, and during World War One, many of Europe's young people died. But I really have no idea. I've never seen any comment on this fact or any speculation or analysis of why it happened. It's a very interesting fact. One other interesting thing that happened, though, between 1913 and 1934 is we began to start using more and more oil, and then I think later gas also. The reason why we did that was because we figured out how to make internal combustion engines, which means the fire occurs inside of the engine instead of in a boiler outside. And the internal combustion engines are the ones that we mostly use now, and the reason why we like them is because they're more compact and they're more powerful. And I'm sure any number of other reasons, and they're the reason why, or they're one of the key reasons why we're able to drive down the road. Before internal combustion engines, you could use an engine to power a train, but some people tried to have steam-powered cars that just didn't work very well. They were enormous and bulky and slow. But once people really figured out how to do it, and then figured out, starting after, anyway, it was in those years of the first decades of the 1900s that the navies of the world figured out that they had to have internal combustion engines in order to keep their navies deadly. It was also during those years that we began to build cars, millions of cars, and at the first, we can't say ordinary people, but at first upper middle class, and then soon enough middle class people began to drive cars, at least in the rich countries, not so much in the other countries. The rich countries, to recap, they're the ones that industrialized first. They were some of the European countries, United States, Canada, Australia. I'm not sure whether that was yet, but Japan industrialized early too. And so we began to use more and more oil, and from 1913 to 1934, the amount of oil that we used multiplied by 2 roughly every 10 years. So even though our total energy use wasn't really changing much, our oil use was going through the roof. And continued going, it continued doubling every 10 years or so until about 1970. So there were, I'd say, at least five doublings from from the 1920s until 1970. In 1970, something happened to our oil, the multiplication of our oil use, which I'll discuss later in this episode. Something very interesting happened to it, but that's basically when the exponential growth of oil ended. Okay, but while the exponential while oil was growing exponentially, it was multiplying by 2 every 10 years, not by 2 every 16 years as coal had done beforehand. And part of that was because we were switching many of our engines from coal to oil, more or less. Um, but also we were finding lots of things we could do with it, like power our airplanes and our tanks and our cars. So in 1934, our exponential growth resumed. Okay, if you look at the total of our energy use, now totaling coal with oil and gas, the next multiplication took 21 years, so a little slower, 1934 to 1955. And then the next doubling took 15 years, so back to the old speed, 1955 to 1970. So we were back at it. Whatever had been missing for 20 years came back into play, and we were going full speed ahead again. I want to say about that pause is, in the real world, you don't get a exactly regular multiplication on a timetable, but you can come pretty close. And if you look at the last 250 years, it has been not too. It has been pretty close to a regular multiplication. There was an interruption. The rest of the time, it's been going on. Now the next doubling after 1970 was a little slower again. 1970 to 2005, we multiplied by 2 again. Okay, and as of now, now it's 2025, we're still multiplying. Not maybe not 15 years, but not too much different than 1970 to 2005 time span. Overall, from 1934 to 2014, in other words, starting just after the pause, our energy use multiplied by 2 every 24 years. If you went back to 1780, or whenever the exponential growth began, somewhere in that window around 1780, you would get a little faster speed because there were more than 100 years where it was doubling every 15 years or so. But then in compensation, there would be the 20 years where it didn't grow at all. But overall, I'm sure you'd get something a little faster than 24 years for our energy use. So I want to say a little bit about human experience. What that means is a generation, at least until recently, it took a generation of the human race was roughly every 24 years. So that means that if you looked at the average across the human race of our energy use, the average parent used half as much energy as their children. That's more or less true. You have to take into account that there were a few more children than there were parents, but it wasn't anything like a multiplication by 2 over 24 years. So roughly speaking, children had and could count on this for roughly 10 generations now, could count on having almost twice as much energy as their parents. But that's only averaging across all countries in the world. There were, of course, a lot of poor people who weren't benefiting from that. And there still are many poor countries with very little energy use. So I would expect that in the richer countries, the multiplication from parent to child of energy use was even faster, but roughly a factor of 2. So that should give you our energy use is the part that we know most about how it grew, but we also know something about our use of foods and crops and our use of minerals. Our data about minerals goes back 120 years or so, and our data about the world food use goes back 60 years or so. So there are many resources that are doubling at about the same speed as our energy use. One is currently our consumption of meat and fish is multiplying by 2 every 25 years. Our consumption of sulfur and nitrogen is multiplying by 2 every 23 years. It's doubling. So quite similar to coal, oil, and gas. I want to say about nitrogen, there was just after World War II, people had figured out how to make fertilizer, nitrogen fertilizer, by burning coal, and they began to use it on a worldwide industrial scale in our farms just after World War II. In something that's called a Green Revolution. Now, I'll discuss the Green Revolution repeatedly, and later in this channel's content, but it involved applying large amounts of nitrogen fertilizer and of other fertilizers to the ground, and you could get using that you could get a nice crop. And so from 1946 to 69, actually, so a little more than 20 years, our use of nitrogen fertilizer was multiplying by 2 every 6 years, not every 23 years. Now after 69, it slowed down to the current 23-year doubling time. But that often happens when something new, when we figure out how to do something new. First there's a period of extremely fast exponential growth, and then later we slow down. So for instance, plastic, which was also invented, the first usable plastics were invented around the same time as nitrogen, a little bit later, and it was multiplying by 2 every 5 years during the 1950s and 1960s, and then it slowed down, and nowadays it multiplies by 2 every 13 years. So still much faster than our energy use. There are a number of other materials that are doubling at about the same rate as our energy use does. Salt, potash, another fertilizer, iron for steel, and aluminum ore. Aluminum ore was multiplying by 2 every 8 years from 1900 to 1973. So that's a huge number of multiplications. It's like it multiplied by, in total, something like 500 by 1973, and now it's slowed down to 20. And whenever you see a slowdown, you can be pretty sure there's a reason for the slowdown, and it probably has to do with a lack of some sort of resource or other. So these are the things, and I'd say overall, it looks to me, looking at all the resources in question that we use, that overall we multiply our use of resources roughly every 22 years. For the last 80 years, energy has been multiplying every 24 years, multiplying by 2 every 24 years. But other resources, roughly it's around 22. It varies, as you can tell. Now there are some that are still going very quickly. Platinum every 16 years. Cement's a big growth industry for building structures. That's been multiplying by 2 every 10 years. Um, uh, so there are some things that are going very quickly, and then there are also some that go quite a bit more slowly. Um, One of them, and when they go more slowly than energy, there's also a reason. Um, One of them, for instance, is cereals. Wheat and corn and rice, and they multiply by two, not every 24 years or every 22 years. They multiply by two every 32 years, and I suspect the main reason why they're going that slowly is because we can't eat any more than we're eating right now. We're already overfed and have major health problems, and we just can't get our bodies any bigger. And so most of the growth in cereals goes to our meat, growing meat. Another one that's growing slowly is gold and silver. We multiply our gold and silver consumption by two every 40 years, and I think the reason is obvious. They're just hard to get. And another one that's interesting is cotton. We've been multiplying that by two every 42 years. Um, uh, and the reason why that multiplies as slowly as it does is because since plastics were invented, plastics have been taking over our clothing and our textiles, and by now 2/3 of our clothing is plastics. So uh, if we didn't have plastic clothing, then by now, then I'm sure that cotton's growth rate would be closer to 20 some years, not 42. So I hope that this nails down for you and leaves you with absolutely no doubt that the human race has been going through an exponential growth, a growth in our regular multiplication of our resource consumption for around 250 years. It's an extraordinary fact. We've never done anything like this before. It's completely changed what life is like for us, and has completely changed the face of the planet. It continues to change it. And I just wanted to make it absolutely solid so there's no questions about it. I'm going to talk some more about exponential growth maybe in the next episode, but these are the numbers. And I think it's very important. I mean, the question is, of course, and I've already mentioned this in previous episodes, how long can we continue multiplying? Every exponential growth, as I've mentioned, ends. When is this going to? When is this one going to end? When are we going to stop? And what will life be like for us when we do stop? After 250 years of this, it's hard to imagine any other way of life, and it sounds like it would be a disaster. But obviously, it's got to end. How's that going to happen? And what's life going to be like after that? That'll be the material of much of the rest of this content. Something I won't discuss a lot is why the exponential growth happened. I've already told you I think exponential growth, when you see it, generally tells you that something very mechanical is happening, something that doesn't involve any thinking. If anything, it involves a complete loss of self-control, or something that never could have controlled itself in the first place, like a bacterium or an atom. So I think already just on the face of it, the datum, the fact that we've been doing exponential growth tells you a lot about why we're doing it and what's involved. And it tells you something very different from the storyline that people have, which is that's because of human ingenuity, hard work, capitalism, whatever you want to call it, whatever reasons you have for our success, we did it. It's because we're amazing people. Um, sure, we can, and then people will give varying reasons about why it's happening. Different people give different accounts, and they will also argue about how it can make it keep happening, or it's somebody's fault if a particular family or country is not multiplying its economy or whatever. But on the face of it, mathematically, looking at the data, there's obviously a guiding hand, maybe an invisible hand, which has been pushing this along. It must be something very simple-minded, and it's and bigger and than. I mean, that's my suspicion. That's the way it is for every other sort of exponential growth. Exponential growth always involves something with no brakes on it, no self-control. Which brings us again to the question of what comes next. If we have no brakes and no self-control about doing exponential growth, is there any way that we can really pretend to begin to prepare for whatever comes next? There's a lot of talk about planning for our future, or for instance, or trying to build a better future. For instance, that's one of the banners that people talk about with green energy. But I mean, if what we've been doing up till now has been characterized by a lack of self-control as a human race, then do we really have any real prospect of making real decisions about what we're going to do next? So that'll be. I'll just leave it out there. Perhaps, perhaps, but the data give you no confidence that this could happen. Okay, with that, I'll close this episode, and thank you for your attention. I hope to make another episode at least every week, and I hope you keep coming back. Yeah, keep coming back. Thanks.